Waves are everywhere around us, from the sound of laughter to the heat from a campfire. But what exactly is a wave? Fundamentally, a wave is a disturbance that travels through space and matter, transferring energy from one place to another without causing any permanent displacement of the medium itself. Think of it like doing the wave in a stadium. Each person stands up and sits down, but the wave moves through the crowd. Waves can be categorized broadly into two types: mechanical waves, which require a medium like water or air to travel through, and electromagnetic waves, which can move through the vacuum of space. The motion of waves is fascinating because it harnesses and transfers energy so effectively, which is why we can hear sounds or see light. Understanding waves helps us grasp everything from basic physics to advanced communications technology. To truly understand waves, we need to explore their characteristics such as amplitude, frequency, wavelength, and their interactions with the environment through reflection, refraction, and diffraction. Each characteristic gives us more insight into the nature of energy and motion in our universe. So let's dive deep into the dynamic world of waves and uncover how they touch every aspect of our lives. Oscillations refer to the repetitive up and down or back and forth motion that forms the basis of wave behavior. When a stone is thrown into a pond, the ripples that form are visual representations of oscillating water particles. The motion starts at the point of impact and spreads outwards, demonstrating how energy travels in a wave pattern. The concept of oscillation is not just limited to water. It happens in air, through the ground, and even in the vacuum of space. A pendulum swinging back and forth is another simple example of an oscillation. Here, the pendulum moves away from its rest position and then back toward it, influenced by gravity and its own momentum, just like particles in a wave. Oscillations are crucial because they are the fundamental movements that give rise to waves. The properties of these oscillations, how fast they happen, how long they last, and how big they are, define the nature of the wave produced. By understanding oscillations, we can predict and manipulate wave behaviors in technology, nature, and daily life. Frequency and period are two fundamental aspects that describe how waves behave over time. Frequency refers to the number of complete oscillations that occur per unit time and is measured in hertz. For instance, a wave with a frequency of 2 Hz completes 2 cycles every second. This is crucial in understanding phenomena like sound pitches and light colors, which are determined by the frequency of waves. The period, on the other hand, is the time it takes for one complete oscillation or cycle to occur. It is the inverse of frequency. For example, if a wave has a frequency of 2 Hz, its period is 0.5 seconds. This concept is essential in designing systems that need to synchronize with wave movements, such as in communication technologies or timing mechanisms in electronic devices. By manipulating frequency and period, we can control how waves interact with various mediums, how they carry information, or how they affect physical systems. From the deep bass of a stereo system to the precise timing of GPS satellites, understanding these concepts is key to harnessing the power of waves in practical applications. Amplitude is a measure of the strength or intensity of a wave, visually represented by the height of the wave. In sound waves, higher amplitude means louder sound, while in light waves, it influences brightness. Amplitude is fundamentally about how much energy is carried by the wave, which affects how we perceive and utilize different types of waves. The crest and the trough are the peak and the lowest points of a wave, respectively. When you look at ocean waves, the highest part that often curls and breaks is the crest, and the lowest part between each wave is the trough. These points help in visually understanding the amplitude and also in measuring it, as amplitude is the distance from the rest position to the crest or the trough. Understanding these elements helps in various practical applications, from engineering safer ships that can handle high sea waves, to designing better acoustic systems that can accurately capture and reproduce sound. The amplitude, crest, and trough are essential for not only understanding, but also manipulating how waves behave in different environments. Section 5. Wavelength and waveform, the shape of motion. Wavelength is the distance between consecutive corresponding points of a wave, such as from crest to crest or trough to trough. This measurement is crucial in understanding the type and behavior of waves. For example, shorter wavelengths correspond to higher energy in electromagnetic waves. The wavelength determines many properties of waves, such as their ability to diffract around obstacles or their propagation speed in different mediums. Waveform, or the shape of the wave, tells us more about the energy and direction of a wave. For instance, sine waves represent a periodic oscillation of a single frequency, commonly found in acoustics and electronics. The form of a wave can be complex, combining multiple frequencies and amplitudes, which is typical in natural settings like ocean waves or in music. By studying wavelength and waveform, scientists and engineers can design systems that use waves more efficiently, such as antennas that need to capture radio waves, or acoustic systems that optimize sound clarity. Understanding these concepts is key to leveraging the full potential of wave-based technologies. Section 6. Understanding phase in waves. Phase in waves refers to the relative position of one point in a wave cycle to another. It is crucial when combining waves to understand how they will interact, whether they will strengthen each other, known as constructive interference, or cancel each other out, known as destructive interference. For example, if two waves are in phase, their crests and troughs align and they add up to create a wave of higher amplitude. Understanding phase is also essential in technologies like noise-canceling headphones, where sound waves from the environment are canceled out by generating out-of-phase sound waves. This phase difference creates destructive interference, effectively reducing unwanted noise. Phase differences can be used creatively in various fields, from creating spatial effects in audio engineering to improving signal clarity in telecommunications. By controlling the phase of waves, it is possible to manipulate how they interact and propagate, opening up new possibilities in wave-based applications. Section 7. Mechanical versus electromagnetic waves. The main categories. Mechanical waves and electromagnetic waves represent the two main categories of waves, differentiated primarily by the medium they require to travel. Mechanical waves, such as sound waves or water waves, need a physical medium like air, water, or solid to propagate. They operate based on the oscillation of the particles of the medium, where the particles transfer the energy from one to another. On the other hand, electromagnetic waves, or EM waves, do not require a medium and can travel through the vacuum of space. This category includes visible light, radio waves, X-rays, and more. These waves are generated by the movement of charged particles and are characterized by their electric and magnetic fields, oscillating perpendicular to each other and to the direction of wave propagation. Understanding the differences between these two types of waves is crucial for applications ranging from medical imaging using X-rays to communication technologies using radio waves. Each type of wave has unique properties that make it suitable for specific applications, and knowing these can help in designing more effective and efficient technologies. Section 8. Dive into radio waves, infrared, and ultraviolet light. Radio waves with their long wavelengths are used extensively in communication technologies, from television broadcasting to mobile phone signals. They are excellent for long-distance transmission and are less affected by atmospheric conditions compared to higher frequency waves. Infrared radiation, which is just beyond the visible spectrum, is primarily associated with heat. It is used in various applications, such as thermal imaging cameras, which can detect people or objects based on the heat they emit, and in remote controls, where short-range signals control devices without the need for wires. Ultraviolet light, with even shorter wavelengths, carries more energy and is known for its ability to cause sunburns. However, it is also utilized beneficially in sterilization processes, where its high energy destroys bacterial and viral DNA, and in forensic sciences to detect substances invisible to the naked eye. Understanding these different types of electromagnetic waves opens up a myriad of applications, from everyday conveniences to critical medical and scientific tools, highlighting the versatility and importance of wave science.